And perfect. So I would like to welcome you all on today's session of Train the Trainer. All these efforts and organization is coming from different projects like CASTIEL 2. I'm also coming from CASTIEL 2 together with my colleague here, Sima and Tobias. We have a huge organization also from the side of Europe, CC2, Cineca, and Barcelona Supercomputing Center. As you know, this workshop will be taken online. All the communication will be through Discord. So afterwards, I will also show you how to use Discord, but maybe you had opportunity already to sneak around. Multi-GPU AI Train the Trainer workshop will start from today until 5th of February, always starting from 9:30 a.m. until 5:30 p.m. Central European time. And we will try to keep some lunch break between 1 to 2 p.m. Please understand that some sessions maybe will be longer or shorter, so let's try to keep the flexibility because some of the sessions might have some issues with the access or extra questions. So thank you for your flexibility. What to expect today? So from the day one in the morning, we will start with NCC Italy, Alberto Bocchinfuso, and he will be talking about introduction to GPU architecture, access to HPC infrastructure. After lunch, we will have trainers from NCC Sweden, Ashwin, Mohanan, and Yonglei, Wang. They will be also talking about another interesting topics, basic deep learning tasks from CPUs to GPUs, and introduction to deep learning. So I would like to thank you all for being here and for participating in this workshop. I hope you will stay with us until the end of workshop and that you will enjoy this training. Also about Discord, I would like to share my screen. We already started to chat there, so you can see.
This will be very hands-on, so it is very brief, and feel free to stop me, but even better if you can simply wait for the end of the presentation, which will come relatively soon because it's short, and then we try and see if you are able to, do what you need, which means using the Jupyter notebook and all the rest. So I think I can go in presentation mode and we can start. So the point of this short presentation is to understand how to use Jupyter on Leonardo. As you know, Jupyter is made out of a kernel, which is a program that takes your instruction, which is somewhere. In general, it is on your laptop, but if you want to use another computer, I will show you how to do it. And there are certain pre-requirements for use it on Cineca HPC. We will start with the passwordless login between nodes. And then we will learn how to launch the kernel and connect to the kernel. There are also additional resources of which I want to make you aware. Of course, I think you will use this big part here in this instance, but we've got additional resources if you want to do some advanced things, maybe in automatic. So I told you that you cannot SSH to compute nodes, which is true. You cannot simply enter the machine and then SSH into this or that node while another user is using. And of course, Zoom is aware of what nodes are free and what not, also because nobody can do whatever they want. But you can use SSH to go into a compute node that has already been given to you by Zoom. Basically, you get your node and you can SSH into it. The point is that if you try that right now, you will get a permission denied. There is no way of using a password on Leonardo. Okay, if at some point Leonardo asks you for your password, push Ctrl C because you're doing something wrong. Even for SSH, of course, the nodes want some authentication, but you can only use a key. Again, this will be very hands-on, so I encourage you to try that at least after I've done speaking about this. But you use SSH keygen, which probably you have already done that in your life, in other instances. And this is used to create a key. Of course, leave it without password. This is your key, is on a protected machine. There is no need for a password. And also the programs themselves, not only Jupyter, it's more general. We'll use this key to connect among nodes. So not all programs need it, but certain programs need it. So no password. Basically, you create your key. And I know that many of you are used to do the copy ID, which is the correct procedure to the remote machines. But on Leonardo, you can simply write this line. If you know your bash, you will understand that we are simply copying to the authorized key file the public part of the key that we've just created. At this point, if you try to SSH, you will get into the node. Well, first you have to have your job running, otherwise it will not work. But this is the outline. So this is a very important requirement because we don't allow for password use on Leonardo, only keys. So now you want to use Jupyter. If you want to use Jupyter, you have to install the requirements. I don't know about the experience with Python that everybody has got here, but it's clear that you have to have a virtual env. So my suggestion is make an example folder for this class. The requirements will be given to you by Eleonora. I think I wrote in my requirement file simply Jupyter Notebook. And load a module with Python for Python. I suggest you 3.11.7. I think it's the last version that we've got on the cluster, and it can be loaded directly from the module base, so from the profile base. So you enter the cluster, you have it. Create the env, activate the env. I guess most of you, if not all of you, know how to do this. And install the requirements. Depending on what you write on your requirements, it can be very slow or very fast. If you already Jupyter Notebook, it's something to download, but in general, it is anyway, it is a small thing enough that we can do it on a login node without disrupting operations. So you can do this on login nodes. Now, you see something very similar to what I've shown you in the other presentation. This is a submission script for Zoom. Everything like before, we are asking for 2 nodes, 1 task per node, 8 CPUs per task, which means 8 CPU for every GPU. we ask for 1 GPU, 2 nodes, 8 CPUs. This is 1/4 of a node for each, if you want to try copy pasting these actually. Oh, I think I have to give this to Eleonora. I will give them later. So use the boosted partition. If it is just a test, use the debug. This is the wrong account. Sorry, you will know what is your account. This activates the environment that you just created. I am taking it for granted that you will launch the script from the folder. And we've got all these strange lines here. They speak with the Slurm controller to understand what is the head node of your job, because it runs on 2 nodes. It's a very interesting exercise. It selects a random port, and it creates an SSH tunnel, basically, from the login to the head node of your job, which is running on 2 nodes. And then it will tell you that you have to connect to this address to see your Jupyter notebook running. This srun line here really launches the Jupyter notebook itself. So before connecting to this notebook, which is listening on the specific compute node that was given to you, at least the head of your job, you have to open a tunnel via SSH. Now, as I've told you, you cannot reach the compute nodes from outside. You can only reach the login node. So we will make 2 tunnels, and this is the command to do that. You open a tunnel from your workstation to the Leonardo login. You open a tunnel from the Leonardo login to the head node, and then you will be able to connect through this machine, so your workstation. SSH will take care of handling the traffic and forward it to the login, to the head node of your job, and you will have your kernel running. The script on the previous pages kindly echoes the command that you have to write. The HTTP address is already filled in, so you don't have to substitute the variables yourself. And read the Zoom job ID. And very last recommendation. You are opening 2 tunnels from one computer to the other. Please be mindful of those tunnels. Do not send them to background, never. If you can remember the PID of the process on your machine, it's even better. Remember to stop them at some point when you don't need them anymore, because of course a port is still a resource. So, and also you will not be able to bind any other program to that specific port. So it is in everybody's interest that you are very mindful when you launch a command like this. Okay, so if the process is working in the way it is meant to work, you will have your Jupyter notebook on your machine. So now, again, I will keep it very brief, and then you can start experiment with this. I think we've got quite some time before lunch break, but everybody suggested me to give importance to this part so that we are, sure that everybody can do what they have with the machine. So I'll show you before going to the exercise part when you will do your thing with your notebooks. I show you 2 additional resources that Cineca offers to you to automate this process. I think the simplest of the 2 is Japiner. It's a Cineca tool by Fabio Pitari, a colleague in the group of cloud resources, I believe. It is open source, you can audit the source, you can download it, but you can even just pip install the tool. It is a thing that is installed with pip and uses Python basically. It is able to open and manage a Jupyter session through SSH. I was told that there are some problems with Windows PowerShell, but maybe those problems were fixed. I don't know. It is basically, it doesn't do anything crazy. It is everything that I explained you so far, but instead of using this manual procedure, you let Jupyter do it for you. You put your user, the cluster Leonardo, and the tool Jupyter. Jupyter is very nice. It allows you to use many tools. You can check the documentation, of course. So this is the result. You've got your VM in your local machine with Jupyter inside, and Jupyter will launch a job for you and this and that. And at some point, if you select the tool Jupyter, you will get the famous URL that you can click and open into your browser. Another resource that we have, I consider this to be a little bit more advanced, maybe. By me and my colleague Attilio Marcelli, we've got a template to debug code written in Python and use Jupyter Notebook. The relevant part for this class, I was told, is the Jupyter Notebook part on the cluster. In this case, you log into the login node with Visual Studio. I don't know if you know how to do it, but it's one of my favorite way of logging into the machine because it gives you the programming environment, a lot of terminals. You can basically open as many terminals as you want on the machine. It's nice. And the automation that we give you also open source. You can audit the code. You find it here on Cineca GitLab. You will be able to automatically launch the Jupyter kernel and connect to it. We don't use an external web browser. It's everything in Visual Studio Code. So if you download our bit difficult to do it just we also offer extensive documentation just like Fabio. We take issues on GitLab if you find any issue with that. So thank you for helping us. And this is what happens. You open our template, you create the .vemb environment. I think the name is hard-coded, so use .vemb, please, if you use. You start the Jupyter kernel via this script, so we do everything for you. You output this URL here. You go to select kernel, you follow the steps and put the URL inside, and then you open our example notebook, but of course you can put your own, and you will discover that the kernel is executed on the remote machine. So you can disregard the last part for Chapiner and especially Visual Studio Code if you're not interested. If you are, please check our documentation, both for us and Fabio's work. And I will send the slides to Eleonora. I will briefly stop sharing and then I will start again with, So I think I'm sharing a slide. This is the first thing you have to be able to do. You have to be able to log in with SSH among the login and the compute node. So first you first you do the procedure to allow for this possibility to happen. Like this, SSH keygen and all the rest. And then you launch a small task and try to SSH from another terminal, because of course, if you do srun, then you are already on your, and you do your SSH from another terminal, even another login, if you are selected to go to another login, and to the compute nodes you were assigned. Somebody give me some feedback, please. Is everybody able to do a simple launch? Okay, I'm on login one. Try the SSH, but code connection closed. Port. Okay, yes, probably because you don't have an active job. I think I gave the second presentation to Eleonora. For those who received the account. So, where am I supposed to put presentations? Maybe official resources, because Eleonora put the first one in official resources. Let's do this.
Yes, I'm uploading also the last presentation you sent me in the official resources channel on Discord. Yeah,
Okay.
just 1 second, sorry, but yes.
Okay, I think I did it. Okay, nice. So, uh, for Lilia, as I was telling you, you cannot simply go on a node. You have to start a job, and after you have started the job, you can SSH into only the node where your job is running.
Alberto, pardon.
Yes?
I'm sorry. Do we have to use our account with as our username, or is it a different account? I'm sorry, I got lost there.
Oh, okay. Very nice question. I unfortunately Zoom is confusing on this, but it is so deeply rooted that it will never be changed. So you've got a username which is I think cbine00 something like this. Ah no, sorry, because you're not one of our users. Maybe you are using the training account.
Yes.
It will be tra something. That is
Yes.
your username for today, while the account is tra26 underscore castiel 2. I wrote it in the chat. If
Okay.
you see, I wrote in the Zoom chat, sran ta 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 ta. This
Oh,
is a
great.
little help
Great.
that I give you. So the account intended like the project you are building is the training account that you see after the big A.
Okay. Thanks.
If you copy paste this command, hopefully you are given a interactive job. If you tell me what channel to use, because unfortunately I'm not good um, with Discord, I can copy paste it into Discord too. It's not a problem.
Same here. Discord is new for me.
So is anybody having problems? If you've done with that, you can tell me and we will do something, some other, we will go on with the Jupyter thing. But if you're not done, we can wait. So please give me feedback at some point. Okay. Let's see if you can see my console. This is what I want you to do. You start your job. You know that you are on this node because you are asking only for one node. You must be able to do this. Let's see if I can do it. Yes. Okay. So I am in Leonardo 3288 with both my consoles. But if the master console, which is the one from which I launched the script, so the one on the left, exits, then nothing happens to me because I've got powers that you don't have. But you will be kicked out, I promise. You will be kicked out of the node, but I am not because I'm an operator. But yes. So let me zoom a little bit. You must be able to do SSH into the node that you were assigned. If you cannot do this, everything else you attempt will not be successful. Let me check this. Any feedback, problems? You've done it? You find the exercise simple, difficult? Anyone?
This is Cedric again, and not, sorry, Alberto. Trying to SSH into the node where my job was launched. I get that SSH could not resolve host name with the node name.
Oh.
Yep. So bit surprised.
So if you're comfortable, exchange. So we are on the left terminal on Leonardo, and we will call it first terminal for simplicity. I do the SRAN that I showed you, and very fast because we've got resources for the training. I am given a no. I am here. I can do NVIDIA's me, is it? And check the GPU that I was assigned to. But this is not relevant. So then I do SSH LRDN0302 because that is the node that I was given. And I enter the node that I was given. If you do exit here, you will be kicked out of the other node. It doesn't happen to me because I've got powers that you don't have, but this is the point.
Right.
You did it?
No, it doesn't work. So I have to start again. Yes, I'm just exiting.
Okay, but is
I
it?
have a job in the queue, so I know my node name, no problem.
Okay.
It's a bash job, the same one you give us as an example, so that's fine. So I'm just going to log in again. In the second node, this time I'm on login 7.
Okay. And you know the node that you've been assigned to from the job? So there are people that are already running Jupyter. Fantastic. Okay. But we have to solve all these problems.
Okay, so LRND. No, did not resolve the name. Not sure. Okay, it might be because
You could do it.
no, might be because my key was not correctly.
That is fantastic. The key thing is solved in a blink. You simply do this that I show you in the slide. I'm sharing you the screen. This was one of the points of the exercises. You can see how to do it. You generate a key with the SSH key.
Yeah, I've done all that. Yeah, it's just that maybe the authorized key was not properly recorded for some reason. I'm not sure.
Okay.
I'll check.
So you do cat SSH ID RSA pub, and you put it into your authorized key. Maybe append it instead of overwriting. Maybe that is one of the problems. Maybe there are other keys too in the authorized keys file.
Yeah, I think that's the problem actually. You probably have a secure redirection which prevents already existing files from being crushed. I have that on my account at BSC. So
okay, so the procedure with cat should work. Like you should be able to do cat.ssh / the name of your public key, and maybe greater dot in the authorized keys file, and that should work. That would be useful if anybody else tells us if they did and how. That would be a useful thing, but I don't know. Maybe people are shy and they don't want to speak. Okay.
I think the .ssh directory has to be created first manually.
Oh, really? That's possible. Yeah, that's very possible. So if you don't have a dot, I think SSH keygen by default should create it. Anyway, you must be sure to have a direct SSH directory that looks like this. Let's see, sorry, I will share my screen. Looks like this. There is the authorized keys file. There are the two keys, my private key, my public key, and the known hosts will be updated by the SSH client by itself. Oh, you may have to change the permission of authorized keys. Yes, very important. 600. Do that. Allora, Alain Fras, we have to use the following for package installation. First, I don't think you can do what you did because you have to create a virtual environment. Now, assuming that you did create a virtual environment and you sourced your virtual environment with source name of the virtual environment being activate, then you can install the modules. Install Jupyter for sure, then Seaborn, Pandas, TensorFlow, PyDot, like I guess they are useful for this class, but maybe Eleonora knows more than me about this. Oh yes, Ashwin Moare, yes. On Leonardo there are also our modules. It is a nice exercise if you want to download it in your own virtual env. But yes, we put your modules, we give you the modules for these things, especially Pandas and TensorFlow. That would be very difficult to have a computer without them.
Okay, sorry about this. I actually re-logged in. I do have the public key correctly inserted into the authorized key file. No problem. The SSH has the correct, the key file authorized keys has correct permission 644.
No, 600.
It should be 600.
Yes, it must be 600. So
Okay.
chmod 600. This is a safety feature which is very interesting. OpenSSH, which is the SSH that we use, I suppose, wants your files to be for yourself only. Now, I don't think anybody is actually able to read your home, so they cannot reach that location anyway. But in general, when you think about it, it's obvious that your key is only yours. So nobody should be able to read it. So yeah, that is a problem. It's a very interesting feature. I myself would have never, thought about it, but thankfully they did.
Okay. Including the public key?
The public key.
Doesn't matter. Doesn't matter. Yeah.
You did it?
No, it doesn't matter. Whether it's 644 or 600. So I put everything to 600.
Okay. And is it working now?
No. I'll try again.
Mm.
It's very strange.
The authorized keys file has to be 600 and the .ssh has to be 700.
Okay, yeah, it's a directory, yes. Very strange.
So I don't know if most people were able to do that. I guess many people are also already creating their environment. If you want to load Cinec AI, like Eleonora is suggesting, you can, Otherwise, I will share you the slide to create a band for yourself. See,
Alberto.
if you want to create a virtual amp, you can do it in the way I indicated. You didn't receive any requirement from me, but I'm not too worried about it because I see that everybody is having a very long list of things that they want to install. So you know that you want to install Jupyter and all the rest. You can even try to load the Genec AI and tell us if it works or if there are problems. So I am still here. So if some of you unmute themselves and speak, I can help with the problems.
Where do we get requirements example from? Hello?
Sorry, I think I was unmuted. I was answering Santiago, I think, made me the question. Where is the required? Oh, sorry. I've spoken for 10 minutes without. So, where is the
Sorry.
requirement? No, it's my fault for muting myself. I will give you the requirement file that Eleonora sent me on Discord. It's going to Discord right now. But I don't think it's very important. So a requirement file, it's just a list of modules that you want to install with pip. Okay?
Yeah,
So,
I know that, but I
so
wondering if we will need it in a specific set of
you
modules.
can check out on Discord the one that Eleonora sent me. I guess it will be useful in this course.
Okay.
But I don't really know. There are a lot of modules. I just, without auditing it, I just installed it because Eleonora gave it to me and I didn't look at that. It's very long. It's also for the purpose of this class, even if you just write Jupyter and maybe pandas, maybe NumPy, maybe SciPy, that would be already enough. But yes, you can find it full in the Discord right now. Sorry. I was trying to answer you. I promise I was, but like I was muted.
These things happen.
sorry, Tra26 CASTIEL 2, it's your account. As usual, give me feedback. I am trying to look at both the Discord, the channel, the resource channel, I guess. Oh, the HPC access. Okay, there are. Oh, I guess this is the correct chat. Or maybe off topic is the correct chat. I'm wondering. But anyway, the Zoom chat is here. You can unmute yourself and ask. I'm here to help, whatever problem you have. We've got roughly 1 hour, so I think we can do it. If we end sooner than 1 p.m., then we can go and have lunch sooner. If you need me here until 1 p.m. because even just one person is not able to do the Jupiter trick, I can stay here until 1, it's not a problem. How do I say that? My browser with the Jupyter notebook open. So, first thing first, I did launch the job. You don't have to trust me. I ran SQMe. I've got this job. It is on 2 different nodes, Leonardo 48 and Leonardo 60. You can see my user, the name of the job, I called it Jupyter something. The job ID is this one. Job ID. I read the output of this job. The output is Slurm 331, basically my job name. Sorry, my job ID. The name is the one that we use. The ID is the one that the machines use. I go on top of this output file and I find that I have to open a tunnel with SSH from port 60,080. I didn't select it, randomly chosen, so very safe. The head node of my task is node 48. For simplicity, we redirect port 6080 to port 6080. Now, this is my login to Leonardo, yours will be different. And then I will do -n. I think -n means I don't need a shell. I think this is the meaning, but don't quote me on that. I'm not an expert.
Excuse me, Alberto.
Yeah, sure.
Could you please go a little earlier in the process because I'm currently not able to launch my job.
Okay. So I think it's nice.
It says cannot execute Jupyter, and it doesn't let me go forward.
So did you load the environment? How did you call the environment, and have you got Jupyter installed?
There is a code environment in the dos.sh file with the code you provided us.
Yes, and did you call your environment with the same name of my environment? I think mine is called Venv. Did you call Venv also yours?
I think I did that as well because I have a Venv folder that I guess is the Python environment. Yeah, I named the same. as you did.
Okay. Let us know when you're ready. Like we've got a lot of time, and we were anticipating that it is difficult, especially when we're not in person. Unfortunately, remote things are nice, but sometimes in person it's faster the interaction. So whoever has got problems, unmute yourself. I will do everything to help you. And when I do.
I launch the Slurm sh script with tra25 underscore CASTIEL2 as a count. Is that correct?
25, 26, I think. Tra 26, Castiel 2.
Okay.
Sorry, my connection went away. So maybe if you answer me, I didn't.
My job is no more cancelled. My tunnel starts going crazy. I cannot connect. Control C, I stop the tunnel. Please don't send them to background. Control C, you stop the operation. Okay? Now, Cedric, please try again. Probably I was
still on
probably.
the same problem. Can I run more than one job in this session?
I don't know. It's
Because I
possible.
have my previous job, the one that I created to actually try out the SSH directly to the compute
Okay.
node.
Probably
is
cancel that.
still running. Yes. Okay.
Yeah, do exit from that. Probably that might be the problem.
And if I can add, please stop your job to release your resources. Otherwise, you still consume budgets and resources, although you don't have maybe a notebook open. So please remember to stop any job you have running once you are not using the notebook. And I don't know if Santiago is still here.
Let's start with two nicely white screens. So, I'm in lezione esempio, like example lectures in Italian, and I activated my event. The directory is done like this. These are two different jobs that I have run in the past. This one is today. So my batch script is called Jupyter's Lure. Very possible that you selected another name, which is probably a little bit more original than mine. And I launch it. and this says, I submitted this job. This job has got this name. Let's see what the job is doing. Well, first of all, let's see if the job is running. Excuse me. It is. We are already running. And we are running on 2913, 2917. Nice that I can see it, but I don't need to see it because I printed it for myself. So, cat Zurm 33, let's see, 33169. Okay, this is the job. There are all these login information for Jupyter, but on top, I can see automatically the correct command to open the double tunnel. We will send 50190 from my head node LRTN2913 to the same port, so port here, port on LRTN, whatever. This is my account and the address for the login of Leonardo. -N, I think, means I don't need a shell with this tunnel that I'm opening. It's just a tunnel. Please don't send them to background. I know I am repeating myself a lot, but it's very, very important. And I'd say I start the tunnel. So I don't know if you were looking at my screen back then, but I did try that already. And when I lost connection because I canceled my own task, it was saying error, I cannot reach it, I cannot reach it. Here, I don't see that. I see some warning, but there is no error. So I open my Firefox, I go here, the line below, and ask Firefox to open with HTTP my computer, so my workstation, port 50190. So this is the token that you see afterwards. It's a password so that nobody can use your Jupyter notebook, even if they discover the port when it is running. So you see that I connect to localhost, my machine, on this port. The process that is listening on this port is this tunnel. This tunnel will redirect it to port 50190. They could be two different ports. Just, for simplicity, we select the same port on my machine and on the node, and we go through login Leonardo Cineca IT. Actually, to be honest with you, I don't even know on what login I am doing this bridge. I can discover it, but I don't need to know. So copy paste, and Jupyter will appear. Now, I'm not quite good with kernels, but if I open a terminal, which I can, what happens if I write hostname? Okay. Hostname is not the name of my machine, is not the name of a login or Leonardo. Hostname is the head node of my job, 2913. And this is the result that you want, basically. So now I want to do another experiment because I did it some 20 minutes ago. I terminated my task and my job, sorry, and the tunnel went crazy. What if I stop the tunnel? There is this double tunnel here. I do Control C. Perfect. I reload the page, unable to connect. Now, careful and mindful. It is true that the tunnel has stopped. Since I stopped the tunnel, it doesn't mean that I stopped the job. The job is still running. If I create the tunnel again, always with this command, and I could simply do this. Okay. And without sending it to the background ever, please. And do like this. Ole. Same session. Now, this is a training account. The point is that you can leave it going and you can connect from everywhere as long as you know your password. Again, the password for Jupyter is unfortunately seen in the links. Okay, aside from the fact that this is not true, I will show you also this. So if I copy paste this link from another computer with the right tunnel, these two very important lines here, I can connect. But if the kernel is running on our machine, the account gets billed. Not relevant because this is a training account. I discovered that you even have a reservation, so it's nice. But if you are using your budget hours, of course, don't leave it on a compute node because we are billing you. Okay, so before shutting down the job, I will restart Firefox and I will write localhost instead of 127. I don't like it. And the port, I think it's 51090. Now I discover it's not, but okay. 50190. Okay, localhost 50190. Oh, it connects. It connects, but what is my password? The password, it's the part after token, it's equal to. So this is the link with the password free. If you don't want to send around the link with the password free, you give localhost port. Again, they must know the port, they must know how to open the double tunnel, but once the tunnel is open, I copy paste that part, and guess what? I am already in my session once again. Okay, this is it. So I shut down the tunnel, I lose connection, I am consuming my resources, which in this case is yours because this class is for you. Let's cancel me, SQ me. There is nothing more running. ANSI, it is CG. If you see something in CG, it means collecting garbage. So the resources are free for you. And I think I'm done. There is nothing else that I want to show you. If you want to use my template or Fabio's
screen, and I hope that everything goes well. If there's some problems about the internet connection, please let me know. And this is the course material we used for the teaching. I will share this link with everyone. It's right here. This is GitHub repository. You can see the double window layout. Later I will use the left one for the lesson materials and the right one for the demo and also the tutorial. And I'll keep it right here. Right, in the afternoon, we will talk about the introduction to deep learning. If you scroll down a little bit, you can see 1A, this is for the afternoon. And we will right here, I will talk about the introduction at the beginning. In 15 minutes, I will also show a demo about how to log in and also run the Jupyter Notebook in the earlier Node Booster. Then we try to launch the Jupyter Notebook on the local computer and run the tutorials during the teaching and also handout exercises. Right. For the first episode, what are we going to do? We are going to understand the basics of deep learning, and we try to explain how a neural network is constructed and to describe what happens inside a single neuron. We should know when and why to use deep learning. And we should become familiar with deep learning workflow and some representative libraries, and then verify the software setup before we run the hands-on tutorials in the next episode. Right, what is deep learning? And actually not only deep learning, we should get familiar with this domain from a large scope, let's say AI. What is AI? AI is the broadest concept. It includes any techniques that enable computers to mimic human intelligence, such as solving the problem, making decisions, and understanding this world. Machine learning is a subset of AI, and it focuses on development of algorithms and the models that enable the computer to learn some patterns from the data, and thereafter to make predictions. And actually, machine learning includes various techniques. And in this episode, I will cover the classification task. And in the next episode, my colleague Ashwin will cover the regression task. Both of them are considered as supervised learning. If we further narrow down this domain, that is deep learning. Deep learning is a specific subset of machine learning. It uses neural network to learn complex patterns in dataset. Deep learning is especially good at working with unstructured data such as images, audios, videos, and also text data. And because of this, it is widely used in areas like image recognition, speech recognition, computer vision, and language processing. I mentioned about this neural network. So what's it? A neural network is a model that is inspired by how human brain works. It is made up of connected units that's called neurons. We can get a close look at what a single neuron works. Here is one. This is one neuron. Each neuron has one or more input. And here you can see we have input from x1 to xn. And usually input data are numbers, can be floating point numbers or integers. For most of the time, a neuron does three main things for us. First is the weighted sum. Yes, I can hit the right one, but later I want to show you that this double window screen. Give me a sec. How about now? Should I increase the font size? Oh, it's too large, might be. Yeah. It's clear? Okay, okay. I'll use this one. So this is a neuron, and the first step is the weighted sum. And it multiplies each input with weight parameter right here, and then add them together. You see, this is the term in this equation. The second is addition of a constant number we call the bias right here to this summation. This is this term in total right here. Then the third step is application of an activation function right here on this output, on this input, so that we can generate one or multiple outputs. So in a simple word, a neural network includes weighted summation right here, and addition of Bayes terms right here, and then application of activation functions to get output. This is the whole process, and for a single neural work. Also, I mentioned about activation function. What's it? You can consider this is a mathematical transformation that converts neurons' input into output signals. Yeah, from this is input, data. This is the output signal from after we apply this activity function. There are many different activity functions, and here I just show some of them. First one is the sigmoid. This function map the input to a smooth output, making it quite popular for binary classification tasks. Like I want to separate cat from dogs, like this. And the next one is ReLU, rectified linear unit. This one, from here, you can see that its output 0 for negative input, and it gives a positive value when the input is greater than 0. Actually, there is that currently ReLU and its various derivatives have become the default choices for lots of frameworks like PyTorch, like TensorFlow, Keras, due to its computational efficiency. Here, I also provide another one about the linear activity function. And actually, this function serves as a reference, showing network behavior without any nonlinear transformations. So this always as a reference and benchmark to see that if we apply linear transformation, how we can, or what we can get from the prediction. All right, this is how a single neuron works. And actually, a single neuron can learn something, but it's quite simple patterns from the data side. But if we combine multiple neurons together into layers, and then we connect layers into a network, we create a powerful framework that is called the neural network. Here is one neural network. It just shows this network consists of 3 layers, one input layer, one output layer, and one hidden layer in between. For the input layer, we have 3 neurons. For hidden layer, we have 4 neurons right here, and output layer, it has 2 neurons. So the input layer receives raw data. It can be the pixel values of images or some numerical values, like measurement from about some features, and it passes this input data to the hidden layer. For the hidden layer, it contains multiple neurons that process the information from input layer and extract some features from the data set. It depends the number of hidden layers in this neural network, and at the beginning of several hidden layers, we extract a high level, basic level of these features, and then as the hidden layer goes deep, and these layers we extract some high level features from the data set. The output layer produces predictions that has a category for classification task, like is it the cat, is it the dog, or a number for a regression task, such as we want to predict the price for a house in the city, or the temperature for the weather forecasting. Right. Here we have some exercises, and I will leave you later to play with the code to see how and how it goes for this code. So for deep learning, we want to know why, what makes deep learning so deep learning. Actually, they say that deep learning was first developed. I mean, MEMS algorithms were developed in 1980s, but was not widely popular due to limitations at that time. Now we know that for deep learning, it has 3 key pillars. For example, data, big data. We need lots of data for this deep learning training. The second, the computer power, like GPU to accelerate the computing. Third one is about algorithm. If we can get a better, good algorithm, we can train this model to get a better performance. Some algorithms like back propagation, which was proposed by Hinden, is Nobel laureate, well, last year or 2 years ago. This algorithm was developed in 1980s, but at that time there was not so many data and also limited computer power. All these restrictions limited the development of deep learning in 1980s, 1990s, or even 20. But since 2010, we can generate huge amounts of data every day because we have cell phone. We can generate lots of data using images, text, audios, videos, whatever you can think about. And also we have the modern GPUs that can train these deep neural networks much faster. And all these advances make deep learning practical and popular. That is why deep learning has grown rapidly since 2010, and now it's still expanding. You will hear lots of buzzwords every day about transformer, about Hugging Face, models, agents, like this. So we know deep learning is quite popular right now, but should we use it for, say, everything? Actually, there's no. Here are some types of problems that deep learning works well. For example, facial recognition, object detection, sentiment analysis, language translation. We all come to these problems every day. For these problems, deep learning is powerful, but I should say this is not magic. It's just the tool to find the patterns in data set, but has no idea what the pattern means. Here are some key categories for problems that can't be solved with deep learning due to inherent limitations. For example, the problems with quite a small amounts of data or poor quality data, we cannot use deep learning for the training. Or for some problems require reasoning and understanding, or we ask the model to explain some phenomena or give us a reason about this. Currently, at least currently, deep learning cannot do this. Probably in the future, it is okay. In addition, there are some other problems that deep learning could technically be applied, but shouldn't be applied, either because of the simplicity of the problem or due to some ethical, practical, or societal concerns. So for your project, if you have a specific problem, you should know that what kind of the problem it is, and should your problem is adaptable to this deep learning, yes or no, or partially. We will come to this topic when we talk about deep learning workflow. Right here. So deep learning workflow, here we list preliminary steps we need to perform a deep learning task. First is to formulate, outline this problem. What is your problem? It is suitable to use deep learning. We mentioned the three categories that deep learning can solve, can't solve, or can solve but shouldn't be applied. Is your question fall into these categories? If yes, which one? So if you can make sure that your problem can be solved and it should be solved using deep learning, then we move to next step to identify what is the input from the data and what is the output. Let's say what you can expect from this model. Do you want to classify dogs from cats, or do you want to predict the price for a house in the city? Once we know what to get from this deep learning task, we can try to collect the data as much as we can. Once we have enough data, we come to the core part of deep learning. We build a neural network from scratch, or we adapt a pre-trained model and calibrate this model to fit our problem. Then we set some hyperparameters like loss or optimizer, loss function or optimizer. I will describe these terms in the next episode when we run this classification task. All right, if everything is ready, we take time to train the model and then make predictions on unseen data to evaluate the model's performance. Here is the evolution of this log function when we train this model and then make predictions. Okay, after the training, if we say model's performance, it's kind of okay, but if there are some space to improve, then we can take a step further to tune model's hyperparameter to get a better performance. This is step 9, to refine the model to get a better performance. And the last step is to finally, if we are satisfied with this model, we can share this model with our colleagues so that they can reuse this model for prediction, or we can deploy this model to some other operating systems like mobile, embedded devices, or even cloud platform, so that more people can use this model for predictions on their specific problems. I should point out that this is a quite general workflow for a deep learning task, and some steps might be missing in real applications. For now, you just need to get familiar with these steps, and we will reinforce them in the next episode using classification and also regression examples. Before I go to the next episode, I will mention something about these popular deep learning libraries. Definitely, there are other I mean Python. These libraries written in Python. Definitely, there are deep learning libraries developed using, say, Julia, Java, Rust, or MATLAB. I'm not going to cover this topic right here. If you're going to know more about it, I think you can try to Google or ask ChatGPT. Is much smarter than me to solve these concerns. Two other standard packages are PyTorch and TensorFlow. Both of them are widely used for deep learning applications like computer vision, natural language processing, and so on. Keras is a high-level library. It was originally developed as an independent library, but now it is a part of TensorFlow. So usually we say we use Keras, we mean we use TensorFlow in the backend. Besides these, there are some other packages. For example, JAX, MXNet, Caffe, Hugging Face Transformers, Fast AI, and these libraries can be used for deep learning applications focusing on specific tasks. You will come to some of these libraries in the following part of this course. Right here, I will have a short demo to show you how to validate the programming environment before we come to the next episode. Right, you can see my screen with the double layout terminal. I will log in the Leonardo booster. Yes, I'm right here. Then I'll come back to this lesson material. If we go back to here, first step 0, set up if you're not running the Leonardo booster. Oh, not this one. Scroll down a little bit. Here are this. I use git clone this GitHub repository, which includes all Jupyter notebooks and also script. Paste right here, and it's downloading this GitHub repo. I see this is the CASTIEL content SE deep learning intro notebook. You can see what I have. This is the Python script. The second is a classification, and the third one is about the monitoring training. Here we have bash script. We ask for some node and GPU hours and some reserved time for this. I submit this one. Oh. As batch start. Take time to generate the token, and then I can use that to launch the local Jupyter notebook in my computer so that I can connect to the computer computational node. We see it here, yes. Slum is here. It takes several seconds. See. It's right here. I copy this one. In this morning, you are quite familiar with this one. So I copy this to another terminal. The green one right here. And then I copy this link to the web browser. I prefer to use this one. See, I come right here. If you see how many files I have, this is the Jupyter notebook for the second episode about the classification task. The third one, the fourth one, and everything's right here. I hope that you can log into this cluster and try to launch the Jupyter notebook at your personal computer. And let's take 3 minutes, might be. Just let me know if you come to any technical issues. In 3 minutes, I will continue to come to the next episode. As I prefer, can you post the gate report? All right, gate report, it is gate clone. Where's my right here? Or you can come to this lesson material. It is at the front page. You can see here. In the next episode, I prefer to use the double web browser layout, because for the left one, I will show this lesson material, and for the right one, I will run this code in this Jupyter notebook. And let's see if we can solve this. Left, right. Does this work to everyone? Okay, thank you. Okay, great. Then I used this layout. About the font size, did this, okay. Yeah. I will wait for 1 minute. I hope that everyone can log into the Linux booster, launch the Jupyter notebook, and also at your local computer, so that you can run these tutorials for this penguins classification task. If you come to any technical issues, please let me know. All right. Hope that everyone can try to log in and launch the notebook at your local computer. I will move on to the next episode about the classification by a neural network using Keras. So in this episode, I will follow the deep learning workflow and perform a classification task using the penguins dataset. I will try to explore the dataset, identify what is input, what is the output, and then perform some data preparation and data preprocessing. Then we build a simple neural network consisting of 3 layers, one input layer, one output layer, and one hidden layer in between. We build this model from scratch using Keras or say TensorFlow. Then we train this model on the penguins dataset and make predictions. We interpret the training process and evaluate this model's performance to see how it works. All right, in this episode, we will keep it simple and just want to show you technically how a simple neural network works. We don't want to go into depth to show how neural networks on the mathematical level. Might be too difficult for us to for the simple understanding. In the next episode, you will come to more concepts like how to monitor the training progress and how to optimize the neural network so as to get a better performance. Right, let's move on. We follow this deep learning workflow. And this, as we mentioned before, to first formulate the problem. What's the problem? We're going to use this penguins dataset for a classification task. I should say that currently we don't need GPU because this dataset is quite small and the classification task is also quite simple. But however, when you want to handle large dataset for quite complex problems, you do need GPU to accelerate this computing. All right, step 1, we will see what is the problem. We will run this classification on this penguins dataset. For this dataset, we can test 3 different species. And here at the right side, I will run this Jupyter notebook. Okay, where we are, this is the Leonardo booster, this is the computer node and the host name. And here to make sure that the limit log information from this TensorFlow. And we verify that these modules are properly loaded. Okay, this is the version scikit-learn TensorFlow Keras. Good. Then we asked for 1 GPU, so to make sure that we have this number of GPU available, 1 GPU, great. All right, then we formulate this problem. We know that we want to predict the penguin species from the physical measurement. First, we load this penguins dataset. We have a penguins dataset.csv file in this directory. If you see, this is one right here. We load this dataset and to see what it contains. There are 7 columns right here, which means 7 features: species, island, and sex. They are category variables. 4 numerical variables, for example, bill length, bill depth, flip length, and body mass. And we see if the shape of these penguins, we have 344 penguin samples right here. But if you see that for some penguins, we have none, means that some physical measurements are missing for this penguin. And actually for deep learning, we have to handle this before we perform the training because the algorithm doesn't want these known values. And we will see this penguin dataset, how it looks like. we plot this pair plot. We have 4 numerical variables. We can see the pair distribution of these 4 numerical variables. From here, these are the 3 penguin species, Adelaide, chain strip, and gentle. From here, you can see that for some pairs, like this one, this is the bill depth, this bill length. It's kind of clear to separate these penguin species. This is also for this one, for this pair. For this, not so good, because for Adelaide and gentle, there are a little bit of overlap. But for these 3 pairs, you can see there are strong overlap between Adelaide and chain strip. Either for this is the flip length or bill depth. This is the body mass or bill depth, and also the body mass or flip length. So for some features, they can be used for a good separation of these 3 penguins. For the other features, maybe not. And we will try to use these features to see how can we separate these 3 penguin species. Right, we know the problem, and what we want to do is to predict the penguin species using these numerical variables. We know the input. Okay, input is this physical variables right here, and the output is the penguin species. It's Adelaide, it's the chain strip, or gentle. We prepare the data. What is we're going to have? We are going to reserve this. We drop this island and this x. We don't need these 2 category variables. And we just left 1, 2, 3, 4 numerical variables and 1 species. Then we drop the rows that have the null values. Yes, it should. Yeah, after we remove this, right here. At the beginning, you can see number 3 is null. Then we remove this penguin species with these null values to make sure that all these penguins in the data set have specific values. Then we separate these features from labels. What is features? Features are input values to this training, to this neural network, and the labels are the target we want to predict. Here we have 4 numerical values, numerical features. They are the features for this task, deep learning task, and here is the target. Because here we have the target, the species, let's say Adelaide, chain strip, and gentle. The computer doesn't know what is Adelaide, what is chain strip. We have to transform them to numerical values like 1, 2, 3, so that the computer can recognize what they need. Next step, in addition to split the data into features and the labels, we should further split this data into training and testing data set. The reason is that when we use training models to make predictions, we should use new or unseen data that is not included in the training data set. The data in this testing data set is reserved just for testing to make sure to validate the model's performance and see how it works. Sometimes we should split the data into 3 parts. I think in the next episode, you will see this. 1 part for the training, 1 part for testing, and the other part for tuning the model's hyperparameters for a better performance. Well, the splitting is quite straightforward. We use this train test split from the scikit-learn to separate these features and the target into 2 groups. And the test size is 20%, which means that 80% of this data for training and 20% for testing. Definitely, you can change this, let's say, 90% for training and 10% for testing. All right, data is ready. Let's build a neural network architecture from scratch using Keras. In order to make sure that we can get the same result each time we run this tutorial, we set two random numbers right here, one for NumPy and one for Keras. Then we construct the three layers: input layer, hidden layer, and output layer. So input layer has the shape of this is the input, and you can guess we have four numerical features right here. So the shape should be 4. And for the hidden layer, it has 10 neurons right here, and the activation function is ReLU, as I mentioned earlier. For the output layer, it has 3 neurons. Why 3? Because we want to predict one penguin which class it belongs to. It's the elderly, it's the chain strip, or gentle. We have 3 target groups. That's why we have that 3 here. Activation function is softmax. This one is similar to the sigmoid. The only difference is that the sigmoid activate function is used for binary classification, and the softmax is used for multi-class classifications. Right, we run this. Extreme we have. Oh, I did not run this one. All right, then we have designed this neural. We combine this together to construct a neural network. It has 3 layers, and the number of neurons in each layer is defined right here. And we see, we print the information for this model to see how this outreach. This is the 4 node in the input layer, 10 neurons in the hidden layer, and the 3 neurons in the output layer. And we can see the number of parameters right here. It shows that we have 83 parameters in total, and these 83 are all of them are trainable parameters. You know why we got 83? And you can go through the lesson material to see how to calculate the number of training material from this constructed neural network. All right, we have designed a neural network. Then we should select appropriate tools like loss function. This loss function tells us how good or bad a model's prediction is. Here we choose categorical cross entropy right here, which works well in combination with the softmax, we chose earlier. Another tool is here, we choose optimizer. We saw that we have 83 trainable parameters, and how to tune these parameters to get a better performance. It will be an optimizer's task to tune these parameters. Keras gave a bunch of optimizers and select the popular one. Here we select the most popular one, Adam. It works well for most of the problems. Then we combine the loss function and the optimizer together using this compile function right here. This compile a model means that we tell this neural network or this model how to learn and how to update the model's parameters, and also how to measure the quality of this update. Is the update good or not so good? We run this. All right, we come to number 6. Data is ready, model has been constructed, and the loss function optimizer are defined. Let's train the model. See, it is working. training is super straightforward. We use the fit method here, and the input arguments of features for training, and the labels for training, and the number of epochs right here. Here, one epoch means that every sample in this training dataset has been shown to this neural network and used to update the parameters. For a small dataset like we use right here, an epoch can be just the same as one step. If you have a large dataset, they are totally different, and there are more advanced techniques to design these epochs, and also to design batch or mini batch. I mean, each time what kind of amount of data is transferred to this neural network, so that neural network can update these trainable parameters. Okay. This fit method returns a history object with the training loss and matrices per training epoch. We can visualize this later and see if the training is done. We can see the loss at the first step. First step is 600 and gradually decrease. So as the training progress, is the progress to minimize the loss function. Okay, then we plot this. See, okay, this is the loss function, and gradually sharply decrease, and then come to this plateau, or quite a slow decrease. It means that the training in the first 8 or 10 steps is quite good, and later they come to quite a slow training for this slow decrease in this loss function. So as the number of epochs increase, model tries to minimize the loss function. This means that the difference of true values and the predictions become smaller. This is exactly what we expect. All right, I come to this number step 6 step. I think it's take time for us to perform these tutorials by yourself to see if how you can get when you run this tutorial from step 1 to step 6. Let's say perform this tutorial for 50 minutes. We come back 3 o'clock. Then we will move on to the following steps from number 7 to number 10. Let me know if you have any issues about this technical running Jupyter notebooks, login, or others. Right here. It belongs to Adley, and 0% it belongs to chain strip, and almost 0% it comes to gentle. So for sure, this one could be Adley. And if you see the fourth one, which means that 26% it belongs to, it is Adley, and 0% this is chain strip, and 73% is gentle. And from this probability, we can figure out that this one is a gentle penguin right here. Then we use this IDX max to select this probabilities with the most probable ones right here. You see, this is the predicted species for each penguin in the testing dataset. All right, we have made the prediction, but how can we know that the prediction is true or not true? Then we make a comparison with the label with the true value in the testing dataset. Measure the here we create a confusion matrix here, but here it seems not easy to crack from this matrix. So we want to convert this confusion matrix to a dependent data frame, and then we see how it, okay, this is much more clear. This is the true label, this is predicted label, and some numbers right here. But actually, we would like to use visualization to visualize how it looks like. Here we create the confusion matrix, this right here. Now it is quite clear. This is the predicted labels. This is the true labels. We know the ground truth. For the true labels, we have 30 idly right here. 18 plus 10, 28 plus 2, 13, 30, 30 means, but 18 was identified as idly. This is valid. 10 was identified as a chain strip. This is not so good. It means not valid. 2 of them identified as gentle. This is not valid. Here that's in 30 penguins, idly penguins, only 18 were identified as idly. This is the ground truth. Let's say this is 50 or approximately 70%. For the chain strip, we have 14 right here, but all of them are identified as gentle. This is the totally not so good. Come to the third one, gentle. I have 25 right here. Only 7 of them were identified as gentle, and 18 of them were identified as idly. Okay, this is the prediction from this training model. We can say that the training is definitely not so good. What's the problem? Most problem might be that we have quite limited data in the training data side, and probably some hyperparameters for the neural network and some others. But the model is somewhat okay. We need to refine this model. We think this the performance is some kind of acceptable, but we should move on to refine this model to fine-tune these hyperparameters so that we can get a model with a better performance. Here are number of suggestions. For example, we change the number of samples in the training and the testing data side. Previously, we select 20, 80, 20, means 80% for the training and 20% for testing. And we can choose 90, 10, 90% of this data for training and 10% for testing. In the neural network, we only have one hidden layer. And in this hidden layer, it has 10 neurons. And we can increase the number of hidden layers between input layer and output layer. And also we can increase the number of neurons in each hidden layer. You will see how it works if we're going to increase the number of hidden layers and the number of neurons in hidden layer. Keep in mind that don't change the number of neurons in input and output layers. Do you know why about this? For this data set, we only have 4 features, which means that the input layer has to keep 4 neurons in the input layer. And for these penguins, it has 3 species, idly, chain strip, and gentle. So the number of neurons in the output layer has to be 3 because it has 3 penguin species. For the hidden layers, you can change the number of hidden layers and the number of neurons in each hidden layer. You can get whatever number you want, and you can see if you increase the number of hidden layers and the number of neurons in each hidden layer, you can get a totally different result. Probably you can increase the model's performance. All right, we choose the activation function. For the hidden layer, we choose ReLU. For the output layer, we choose softmax, but probably we can try to the others, derivative of ReLU or some others. About the loss function optimizer, we choose this loss function, cross entropy, and for this entropy, yeah, drop out, great. And for the optimizer, we use Adam. We said that this is the popular one. It works well for most problems. Try to use the others to see how to use another optimizer or loss function if you can get something different. And as mentioned in the chat box, you can use dropout, which means that here we constructed a fully connected neural network, which means that for the 2 consecutive layers, each neuron in the are fully connected to the neurons in the next layer. And yeah, there will be lots of training, but this is the way for this fully connected. And sometimes using dropout means that some connections we drop out this. We don't want this. Sometimes maybe randomly, if you keep ratio, let's say 20% of these connections are cut, then you will see how it looks like. And here we train this model using 100 epochs. Even we saw that the training gets to steady in 10 epochs. But if you see increase the number of epochs, like say 200, especially when you increase the number of hidden layers and number of neurons in each layer, you definitely need a larger number of training epochs so that you can get a better performance. Right. Take the exercises at this nice type and using varied combinations of these hyperparameters to see how can you get a better performance of this model. And a better way is that maybe can use lightning. And in next week, I think Wednesday or Thursday, you will come to this episode using lightning to talk about PyTorch to find for each training, you can keep the hyperparameters and later to combine this performance of these models to see which one is better than the others. Right. Last step is the shared model. Once you get the model with, let's say, with a good performance, you can save it and share it with colleagues so that they can reuse these models for prediction. Or we can save a model for later training. Yeah, today I just want to save this training currently right here. And tomorrow I want to continue for this training. It's okay, you can save this model so that from in tomorrow, there's no necessary for you to train everything from the beginning. And using this saved model, this is the save for Keras. It's quite straightforward to save this model. Once you save it, you can see that we have a penguin classification. Yes, this one. And with this model, we can reload it. Probably in a couple of days, you want to rerun this training and can load this saved model and continue to perform the training or to make predictions. These are the predictions using this trained model. All right, this is to make this training reproducible, something at least you can save some time for the training, and especially when you try to explore a vast space of hyperparameters to find the best model. All right, this is the end of this episode. And please take time for this, especially for the step 9, to refine this model using combinations of hyperparameters. But before that, I will have a short summary about this episode. So in this episode, we follow the deep learning workflow and perform a classification task using the penguins dataset. We explored the dataset and did some data preparation and preprocessing tasks. For example, we handled the missing values. We removed the penguin samples with non-values, and we encode the category variables. For example, for the species, we encode them into true or false or 1, 2, 3. We split the data into feature and label subset, and also for the training and the testing subset. We constructed a simple fully connected neural network consisting of 3 layers, one input layer consisting of 4 neurons, one output layer consists of 3 neurons, and one hidden layer in between consists of 10 neurons. You can increase the number of hidden layers, include more, and usually you will get a better performance. Then we train this model and evaluate the performance on unseen data. We plotted the training loss function to see how this training progress go. Then we created the confusion matrix and to evaluate the model performance. So task to you is to fine-tune the hyperparameters to improve the model's performance to see if we can get a better performance. Let's say all these penguin species are in the diagonal. Right here means 30 right here, 14 right here, and 25 right here. That's the perfect distribution. Finally, we save this trained model for sharing or for the training in the later stage. This is the end of this episode, and in the next episode, you will see how to monitor the training progress using another regression task. All right, we have 50 minutes. Let's take 50 minutes for this to fine-tune the model hyperparameters so that to see that if you can get a better model. I'll be right here, and if you have any questions. You can leave the message in the chat box or you can speak to me. Well, question, how do we know the optimal range of neurons, number of hidden layers to be used? Perfect. At least for this increased number of epochs, better prediction, Adelaide is okay, Dinto is okay. The chain strip is kind of still large number is not valid. Let's say 10 of 15 is not a valid prediction, but try to perform more training with a larger number of epochs or larger number of hidden layers and neurons to see how it works. Okay, back to the question from Lois. How do we know about the optimal range of neurons and number of hidden layers to be used? Should they be proportional to the number of parameters? For the question, I think that should be related to the number of samples in the training data set. If for this one we have if we remove this try to clean these non-values in the training data set, we can get 333. 80% of them, it will be 260 samples in the training data set. So that for these training parameters, it should be less than this. Otherwise, your model will be tried overfitted. Overfit means that the model will try to memorize everything from this data set, and that is not training, that's the memorize. And when you try to use this model for prediction, you will get a very bad prediction. So for the number of neurons and the number of hidden layers, not only for this one and also for the other algorithms, try to start from a simple model and then gradually increase the complexity of this model until you can observe that if you come something about overfitting, stop right there. So keep this model, I should not say as simple as possible, but just we don't want overfitting from this training. Anyone tell me who has found the one with the most good hyperparameters to have a good separation of idly, chain strip, and gentle? My impression that if it constructs a neural network with 3 hidden layers, you might be get a very good performance. Especially with 100 epochs. Cool. 28, 14, 25. So if you try to type the score for this prediction, it will be 99 point something. Louis, right? If you want to include more hidden layers, you're right. You can simply you can write it hidden layer 1, 2, 3, and hidden layer 1 is the input for hidden layer 2, and the hidden layer 2 is the input for output layer. If you include more, just snap these layers together. Yeah, increase number of hidden layers, number of neurons. So I suppose, Herbert, you use the same number for 100 epochs, right? From this case, it seems that the number of epochs is much more important than the number of hidden layers and neurons. Okay, try to increase the number of epochs, let's say to 1000 to see how it goes. 300. Well, still better than 100 because you see for the I think you change the ratio to be 90% for training and 10% for testing. Question why it is that the loss curves just very rapid convergence, not much improvement over the remaining epochs, but the conversion matrix convert to the diagonals, the change loss is minimal. The reason is that at the first steps, the first epochs, it's the training try to update the parameters. I mean, omega weight parameters and the Bayes terms fluctuate too much. That's why you can get a very sharp decrease of this loss function. But at the later stage, the neural network try to fine tune these parameters so that they can get a better performance. I can say that at the first several epochs, this model trying to find a good range for each weight parameter and the Bayes. Once that for example, for weight parameter omega 1, if that this is in the range from 1 to 2, and in the later 100 epochs, try to fine-tune this parameter within the specific range. That's why even that you see the first sharp right here, and that is totally different functionality right here.
break and welcome back to the final part of this today's session. Before we continue, I would just like to remind you that specifically for those who are running on Leonardo, that while you leave, if you happen to leave early before I finish, that to save your notebooks using the Jupyter interface, there is a save button on top. If you want to keep them for your reference, and then to cancel the jobs so that they don't run indefinitely depending on how much you have requested. So it's not enough to just quit Jupyter Lab, but also to cancel the jobs so that you free the resources for others to use. Right. So just to give a short recap of what we were looking at, in the last session, what we saw was a supervised classification task. We were looking at a data set where our task was to identify particular classes. And we were looking at a tabular data set, and we were following a particular workflow to do that. It started with preparation of the data, exploring it a bit, and then building a model, training it, making a prediction, measuring how good the model is, and finally looking for ways to refine it. In the next episode that I'm going to talk about, we are going for a slightly different task, which is called regression. It's still supervised learning that we are doing. Supervised in the sense that outputs are properly labeled, like what we are trying to predict. And why is it called regression now? So in the previous episode, the things that we are trying to predict were different classes of penguins. But if the thing that we are trying to predict is a continuous value, it becomes a regression task. In both the tasks, what we are trying to find is to find a model which approximates a function which can draw the line between these classes, or in the case of regression, it's some sort of glorified curve fitting, if I may. But we use a neural network because why not? You might wonder that these data sets are too small. Why should we use neural networks? I mean, and I agree with you, like it's not enough, but it's not really needed at this point. But it's just to understand the workflow. So the workflow is what matters, and it's not the question of like, should we use neural network at this point? There might be bigger data sets where the classical machine learning approach for regression might not cut it, and neural networks might be the solution. We will also look into questions like, what is optimization? In the previous episode, we saw something called as Adam optimizer. We took it for granted. Now we'll see a little bit of insight into how optimizers work behind the scenes. We also will try to find ways to monitor the training process, in the sense that we want to end the training process when it's good, and not try to train for too much so that we get the phenomenon which is often termed like overfitting, for example. That's one of the reasons why we would like to monitor it. And some more options, and not just hyperparameter tuning, which is maybe the solution that you went for in the, but some more different ways to improve the architecture, for example. So some other questions that we'll go into, and I will not go in at this point. It's better that you understand while we do this thing. But just to give you an idea, the workflow remains the same. We start by identifying the problem. We look at the data. We create a novel neural network from the scratch. We train it, make classification, measure the performance. So exactly the same workflow, but for an entirely different task, which is regression. So what is the workflow now that we're going to try to solve? It's weather prediction. It's not the weather prediction that you might get in your phones, which is more high quality data, which has 2 dimensions or 3 dimensions in space. And so it's not like that. We are still going to deal with the tabular data set. This tabular data set contains daily weather observations from 11 different cities, and it will have different kinds of quantities that it's being recorded, such as mean temperature, max temperature, min temperature, many different weather-related meteorological quantities. And these will be the columns or features in terms of machine learning language. And the rows will be 1 day each, spanning these years from 2000 to 2010. So that means that you have 10 years, so it's like 3,654 rows, approximately, give or take, and different values for these 11 cities. The objective, so this is the data. What's the objective? The objective is to predict, given the values, the observations for a day, we should predict what will be the number of sunshine hours. So we have, for example, sunshine hours is one of the input parameters, but that is like today's observation. We should be able to predict based on that value what should be the next day's sunshine hours. So all the quantities are properly mentioned, and that's why it's a supervised learning task. And the sunshine hours, it being a number, it doesn't have any classes to do. It makes it a regression task. So sunshine hours can range anywhere from 0 to 24 if it's in the Arctic, I suppose. But we won't set any prescribed limits. Okay. So the first thing to do is to load the data set into a proper data structure. And to view what kind of features do we have. So let's do that. And before I start executing this, let me just remind you to ask your questions in this Q&A channel, because it will be much easier for me to follow the questions and answer them live if possible. And Zoom, it's not that easy because things move around a lot in Zoom chat. Okay, so let me try to open the Jupyter notebook. So if you have it already running, it's this notebook which says, which starts with the number 3, which says monitoring the training process. So I'll start by checking if I'm in a compute node, set this environment variable which controls the messages from TensorFlow. You might still get some log messages. And if you want to silence this, you need to set it to 3. And then I do a small check whether I'm doing this on a CPU or a GPU, and it says that it can see a GPU. So that's good. And now I have the CSV file in my local directory, and that's where I'm loading it from, and not from the website, as here what we're doing above. And it says it has 91 columns. So the first thing to do after loading the data set is to, okay, you can look at the columns, of course, like as I said before, it's a couple of cities, and each city has a set of weather observations recorded per day. And we need to predict and the target that we want to predict is this value for the next day based on. So for example, if this is the observations that we have, like the features that we have. We need to predict that it should be 0 based on this row. That's what we are going to do. We will try to take a look at what the columns are and how much the shape is if everything matches. So let's try to do that. We see that, like I said before, it has 10 years of data, so 1 per day. So that's good. And it has a number of cities recorded. And like before, we could, in principle, do a pair plot at this stage, but the pair plot is going to be so big that it's very hard to find and determine like which is valid or not. So at this point, like let's just skip that and let's just trust that like we put in as much as features possible. Maybe we can leave out these 2 features, which can give it a time dependence. We want our weather forecast model to work independent on which year we are working with or which season. So if we are going to do that, if you're going to leave out the month and date columns, which means we are left with 89 columns, right? Out of this 91 columns. And basal sunshine, it will be our target. So let's try to drop these columns and then we will we'll make a new target column based on basal sunshine. So we'll do that. And then what we're going to do is we're going to we're going to make a shift. So you make the target column which matches the next day. And so, for example, if today is the 30th of January, the target column will start from the 1st of, 31st of January, and so on and so forth. That's why we are going to index it from 1 to the number of rows plus 1. And we will be skipping the last row for our input data set, the training data set, and so on. And we're going to make also a split here. So we're going to choose that we will only use the first 3 years of the whole data set. We are not going to use the 10 years so that we keep the amount of data very small. You can adjust this later on if you want. And at this stage, you might notice that we are doing something more here. And this is part of the main takeaways of this episode, that we are going to split our data into 3, not just 2 as we did. When we split in the previous episode, we were splitting just into a training set and a test set, right? So during the training part, when we called model.fit, the model can only perceive and train based on the training data set. And the test set is kept until the very end to evaluate the performance. So this is how Keras calls it, what is test and training. You might be wondering, like, why is validation? So validation, according to how Keras names it is the test, it is the set of the whole data, which is used live while training. So on the fly, while training, it will continue to measure how much the loss is. And this has a particular use. So we are treating this separately. So we won't use the validation set to do measurement, evaluation of our models, but we will use that on the fly during training to control and monitor the performance. So in order to do that, we call this train test split twice. So first we make a set called holdout, and this holdout set of X data and Y data gets split again into validation and test. I have a question. Why do we keep features from other cities while predicting the sunshine in Basel? Yeah, it's a very good question. And one of the tasks in the end is to skip all that, skip all the weather features from just Basel and then to predict the sunshine. We can, if we have time, please explore that and see if that improves things. But right now we are just putting everything. Maybe we're lucky we have a city which is close to Basel, which has a better number of what the sunshine is going to be the next day or not. Some weather phenomena are local, some are not. So, right. So what we are going to do here is to make a holdout set, which is 1/3, approximately 1/3 of these 3 years, so 1 year. And then we split that into two, creating the validation and the test data sets. Okay. And we can check how many rows are just to so that you understand. And this should be the number of rows. So the training set has 767 days, so approximately 2 years. The test set is, and the validation set should be rather equal, I think. Approximately equal, not exactly, but because it's an odd number, yeah. So the next step is to create a simple, dense, fully connected neural network. But then there is a question here, like, how do we create it? Because now the task is different, right? In the previous episode, what we saw was we were doing a classification task. So for classification task is a peculiar loss function called categorical cross entropy. But here we are doing a regression task, so we can do something very simple because what we are trying to predict is a number. And so a number can have an error easily based on how close the prediction is. So the loss function can be based on what the error is, right? Because we are not trying to predict something complicated like a class label, which has to be converted into a number. We can use the number directly. So for that reason, we have some particular things to keep in mind. We'll come to the question of what the loss function is soon, but let me ask you this question in Discord, like what must be the dimension of input layer? And also the clue lies, for example, if you look at the shape of the training data set. So if you're following along so far, I'll print out the shape for you here so that you can answer it based on the out here. So what should be the, how many neurons should be there in the input layer? Anyone? 89, yes, correct, exactly. Yeah, should be 89. So the input layer should match the number of features. And so that's a simple way. So there is no guesswork there. Otherwise, we cannot transfer the data to the network. So the shape of the input layer should correspond to the number of features. It should be 89. And then the question is like, what kind of activation should we use? So here, in the previous episode, you might have observed that we are using something called softmax. The softmax was used there because we want our one hot encoding to work. So the output should always be between 0 and 1, and they should be normalized between all these three classes. We don't want to do that. I mean, we could, in principle, use something else. We can use something called ReLU activation, which ReLU activation, what it does, it activates from the value of 0. Any positive values, it's activated. Any negative values, it's not. But at this point, at this stage, we are not restricting that. We are keeping the output layer as it is. We are not going to impose any sort of activation function. Definitely, we cannot use sigmoid activation because sigmoid will restrict between, it's a smoothing function between 0 and 1. We don't want our number of hours, sunshine hours, to be restricted to 1. Why would we? And then there is the question like how much if we want to predict, like if we want to add another parameter that we want to predict, like then how many neurons we should use. So if you want to output, let's say, a precipitation bustle in addition to sunshine hours, then the output layer should have 2 neurons. But now we are trying to do for just one parameter, so the output layer should be just 1 neuron. So we understood that the input layer should have the same number of neurons as the number of features that we have, and the output should be the same number of features that we are trying to predict. And the rest is actually arbitrary. So it's up to your experience or your desire to choose how many neurons you want to put. The number of neurons has a direct impact on the number of trainable parameters that we are going for. All right. So the number of features, we are giving this, creating a function to make this convenient, and we are telling that this is the number of columns. So let's do exactly that. So we are creating a model, and if you look at the summary of the model, we see what it has created. It has created a flexible dimension, 89 neurons, and then 150 in the hidden layers, and finally an output layer which has 1 neuron. So very simple model. 2 activation functions in between these 2 layers. No activation function between the final 2 layers. Right. Now comes the part where we are looking at optimization and loss function and gradient descent that we have been piecing before. So we need to choose some sort of function which tells the model which way to train, right? So this can be something like categorical cross entropy like before, but in this case, it's very straightforward because we are trying to predict a single value, and there is the true prediction and the the value the model predicts, right? And there will be an error always. So if you construct a function based on that, which is dependent on all the trainable parameters that we have, which includes weights and biases, we get something like a very strange looking a function which depends on a lot of number of dimensions. But imagine that we just have one weight that is trainable, right? One weight of the neuron. Then if depending on that weight, and all the other weights are frozen, then the loss function, if it's positive semi-definite, it will look like a parabola. If the loss function is always guaranteed to be greater than or equal to 0, that's the meaning of positive semi-definite. A good example of such a loss function in this case of doing regression is mean squared error. And that's exactly what we are trying to use in the next step. So imagine for a given weight of the model, pre-initialize it, we get a particular loss that this particular weight of the neuron gives you a loss which is non-zero. And then we make a small change in the weight. We move to this particular weight, and then when we do that, we see that there is a different loss. Then what gradient descent tries to do is calculates the gradient, the change of loss for the given change of weight, the parameter that we are going for, and tries to move in the opposite direction of the gradient so that the loss reduces. So, and this is done per batch. So every time you pass a batch, this is memorized, and then the optimizer, what it does, it takes care of the smoothing of the corrections to the weight, right? So you can either go for you can also go for per instance of the data set that we are going for. And then you might wonder for every other sample from the data, it goes to it changes all the time, like the weight is changing rapidly. In order to avoid that, we use something like Adam optimizer, which has the property of doing something like a moving average of the corrections. And the step that it takes is one of the parameters that we use. It's called learning rate. So ideally, the step should be small, but not too small. If it's too small, the corrections will be very tiny and it will take many epochs to finish. The step is too big, it might not converge at all. It might bounce around in this loss curve. But we will, and ideally, we can also make this learning rate adaptive, but we won't look into that in this part. So as I mentioned before, this gradient descent has to be done in batches. The number of samples per batch is termed as batch size. So just to check that if you understood correctly, let me try to ask this question in the chat. So what do we do by having an optimizer and setting a loss function? What are we trying to do while training? Minimize yes, correct. So we are trying to minimize the loss function. We are trying to move our parameters in the direction against the gradient so that we check the slope of the loss function, sorry for that, and the weights are adjusted. If the batch size is increased, then what happens is that the number of batches in an epoch goes down because it takes fewer batches in total to cover the whole training data set. But also the memory is increased. And that is because the optimizer that you're using has to memorize, will have the dimension of the batch size. Right? It has to keep track of all the losses that it got corresponding to the batch size. So particularly the optimizer state is bigger, and it has to keep track of all the losses, the gradients, and then make corrections. So now comes the part like what is a loss function? This I've explained it already in a bit. Let me try to wrap up at least until training, and then we go for 10 minutes so you can catch up until here and ask questions. So as I mentioned before, the loss function, it should try to find like which way the errors are looking at based on how much correction that we are doing, the learning rate. And two different values which are positive. Positive loss functions are mean squared error. This ensures it's positive, and also mean absolute error. That's also positive. But the peculiarity is mean square error is the larger, it punishes very large prediction errors more severely. So it can make very larger steps when correcting the weight parameters. So it's a good start. So we go for this loss function. We have to mention this as strings only. And the optimizer that we mentioned, it's Adam optimizer that we are going for, which gives a smoothening behavior. There are more optimizers that you can look in the Keras documentation, but it has good properties, and that's why you see this a lot. Loss function gives you an idea of what the error is, but you can also add other metrics. The metrics are only meant to monitor this, so that it doesn't have a direct impact on how the training goes. But they are stored on the fly, so it's very easy to plot this metric. So you can choose any number of metrics that you want to give. Here we are going to add root mean squared as well to see how much is the error on a non-exaggerated measure, which it will be the mean squared error. And it will have the same number of units as the predicted value, so it will be very easy to compare between our predicted labels that we have. Okay, so let's apply all that. We go directly to this option where we add, this option where we compile the model. And then specify the optimizer, the loss function, and a metric. And then we train. So as you can see, it starts at a very high loss function and it tries to minimize it. And all the metrics are also given. We also prescribe something which we talked about, which is a batch size here. So I'll give you 10 minutes to catch up and ask your questions. So exercises and questions until 4:32 or 32 past the hour, wherever you are. And you can also interrupt me until then while I'm explaining. Okay, so let me try to do it like this so I can do the explanations and running at the same time. All right, so now we have trained the model for a specified number of epochs and for a batch size of 32. One thing to mention here, this batch size has also the impact on setting the sizes of the tensor. When you saw, for example, the model summary before, was it here? Here, you saw that there is a none at each layer, and this none becomes the batch size. So one reason for using powers of 2 as batch size is so that GPUs are often designed to work with such kind of registers which are friendly to powers of 2. So that's why often you see this kind of batch sizes. But now the training is done for 200 epochs. We saw the history, we saved into a particular object history. And we can make a function which plots the history. So we see that it starts out steeply and then keeps on going down. The metric that we choose, which is root mean squared error, is going down. So the error at the end of 200 epochs, it's around 1 sunshine hour. So is that a good model that we are getting? Maybe. But how do we know for sure is to make a prediction. So we have the model with new parameters it has trained. We will pass the input features both for the training and test beds, makes 2 predictions each. And then we create a function which plots the true values of sunshine hours and the predicted values of sunshine hours. Predicted values on the x-axis and the true values on y-axis. So if the predictions were the best that we got, what you should get is a line. It's a line with an angle 45 degrees, right? So that line is what we're trying to plot here. So when we do that, and I'll maybe try to increase the size here a bit. What we are saying is like, okay, it's fairly decently clustered around this 45-degree line. So it looks good if you're just looking at the training set. But we also see some issues that we have. We are getting negative values for predicted sunshine hours. What is a negative hour? Nobody knows. So that's maybe why we might need an activation function at the end. Who knows, that could have fixed it. But at the same time, if this was a super model, the performance would have been the same when we give the part of the data it hasn't seen so far, which is the test set. And when we pass the test set and run a prediction, we see that it's all over the place. Like it's not even close to calling it clustered, right? And if you want to summarize this difference, not by visualization, but to look at a particular metric, we can do that because we have the metrics as well. So we pass model.evaluate, which is RMSE. So if it's the training set that we are looking at, the metric says that the error is less than 1, which is, the error is less than 1 here, 0.87. But based on the test data set, the root mean square error is like 4.3 hours. So as a summary. So what is happening here? Like, can we do better? Right, that's a question, right? Always. We can go for changing the architecture, but so on and so forth. But we can also try to do something simple. So, and once again, I mentioned this before, maybe. So at least in the chat. So what we are seeing here is a classic example of signs of overfitting, which means that the model performs super good when it's just looking at the training data, but when it looks at unseen test data, it completely fails. So the model has only memorized some features which corresponds to the training data. So one way is to set some expectations so that you don't go for optimizing for all eternity. And we can create a base model. A baseline model can be anything. It could be a physical model, some equation that you have, maybe a real weather model if you're working with such kind of data, a CFD model maybe. But for now, we can use a very simple and stupid base model, which says that X test basal sunshine will be the prediction. What does that mean? It means that the number of sunshine hours today is the same as tomorrow. So for example, if we had 2 hours of sunshine today, tomorrow it's going to be 2 hours of sunshine. It's a crude model, but is it better than what we got already? Let's take a look. So we have this baseline prediction, and we see that it already avoids this problem of getting negative sunshine hours as predictions. It has somewhat better clustering, but it's unclear by looking at the graph. But if you look at the RMSE values, we see that it's already better than the current neural network. So for the optimization part, what we should try to do here is set expectations, give a baseline value that you want to beat, and try to work towards that. To give a different example, if the model that you're trying to solve is where a model which says a number is prime or not, a good baseline model will be to say that it's always prime. It's always not prime, right? If it says like this number is not prime all the time, it gives you a rather good error because there are very few prime numbers as you go to larger and larger numbers, just to give a different example. Okay, so what can we do now more to improve the model rather than playing with the architecture? One thing, if you were listening too closely, like we had something called as a validation set that we kept, and we haven't used it so far, right? What's the purpose of this validation set? It's not used for actual training itself. It's just to evaluate and monitor how the training is doing. If we see overfitting, if we see signs of overfitting, we can, in principle, stop it, right? So we are not trying to change the way it trains. We are trying to see if it has a tendency of doing overfitting. So let's try to pass the validation set as well and to do the same training. If you are on a CPU, it might take slightly longer, even though the test set is the set is small, the data set is small. So what do we get after doing this? Already by making no changes to the model, we see that while if we keep training for 200 epochs, the training mean squared error metric keeps going down, and also the loss going down. The validation set is already monitoring the model and telling that now it's not getting better at any new data, right? So if we are checking the validation error and the validation loss, we will be able to stop it somewhere over here and not do overfitting. So what should an ideal training be? An ideal training should be like both validation loss and validation errors go down along with the training loss and error. But here that's true only until, let's say, I don't know, 10 epochs, and then the validation error tries to go up. So we need to stop it before that. Can we do that? And the answer is yes. And that's part of the take home messages here. to use a validation set and to do something with that, which is early stopping. So what is early stopping? Early stopping, before I go to early stopping, of course, there is another way to counteract model fitting, which will be to reduce the number of parameters, but we are not going to look into that. Somebody mentioned dropout. That is also a strategy to reduce the number of parameters. But that is discussed in subsequent episodes in the lesson, which we are not covering today. But we are looking at early stopping. So early stopping, as the name suggests, it looks at the validation loss. And if the validation loss is going up, we can stop. But we don't want to stop as soon as the validation loss starts to pick up. Maybe it's just a blip. Maybe it's just a fluctuation. We will, if we wait a bit, maybe the validation loss will still go down. So we need to add something more, and that's called to avoid these fluctuations of losses. We call that parameter patience. So if the validation loss has not got down for 10 epochs, we stop. And how to plug in that is through callbacks. Keras has, when you do training using model.fit, there is a parameter called callbacks where you can pass early stopping object. And there you tell what to look out for. We say look out for validation loss and wait for 10 epochs before stopping. So let's do that here. Sorry. So we are reinitializing the model. We are adding the early stopping callback over here. So now it should not go as long as 200 data sets, 200 epochs, but rather it stopped prematurely at 35 epochs. And now if we look at the history, we see that it doesn't go so far that the model starts to overfit. So here we can do another prediction at this stage. I don't have this in the notebook, but why not? Let me try to copy that. Hopefully I get the right function. Over here, and then plot predictions. After early stopping, and over here. I make new predictions based on this new model and try to visualize and see if things are better. And I should look at the test set because that's what matters. And Y test. And this is the early stopping. So as you can see now, already there is a improvement. We can take a look at the RMSE values too to see if that is better or not. I should have copied that too. Sorry for that. So we have this and we have this. I'm not sure if this is correct. Maybe. because this has not been computed yet. So disregard that for now. I think we'll come back to that. Okay, but at least we have this. Another thing one could do is to add scaling. So people who are familiar with machine learning might be familiar with this. At least classical machine learning and scikit-learn might be familiar with this operation called using a standard scaler. Using standard scaling means that you are looking at the columns and trying to find out what the standard deviation is and the mean, and try to redistribute the values so that they fit in a Gaussian. And this will give you a more well-behaved behavior, so that the network is not attracted towards the values which have more inherently more what is it called, magnitude. So for example, if the temperatures are, let's say, in Kelvin and sunshine hours are measured in hours, so the number of hours cannot go beyond 24 hours, but always kelvins are measured in somewhere around 300 plus or minus 50. So the kelvins, the temperature looks more stronger features to go for, and they can bias towards that. So by doing scaling, we try to do this normalization. But when you're dealing, usually in deep learning, it's will be a lot of work if the data set is too large. It's not the case here, but for that reason, it's often used. A good intermediate solution is to normalize just the batch. So this is done by adding a layer. It's a layer, but it does not involve any. It's not connected to the usual layers which are used for training. It's only used to scale the input data. So just after the input data, we will add a new layer, which is called batch normalization. And then we train it. But you will also see that it has also some amount of trainable parameters. And that's because this batch normalization has some scaling parameters which adjust after every batch. This batch normalization just after input data, and then we also add early stopping, and then after the training is done, which it is after, sorry, I should make this bigger. After 24 epochs, we see a new model is created now, and we compare this predictions, and we get something better from where we started from. I don't have the equations or the code to compute the RMSE values, but you can find it somewhere up so that if you extract the metrics, you can get the RMSE values. And then we should be able to compare this against the naive baseline sunshine hours that we got. I apologize if I was too fast at this stage, but let's just wrap up and summarize what we learned so far. So we have the main points that you should recognize from this part is that splitting your data set into 3 is very important, and it has different purposes. The validation set in particular has the ability to allow you to monitor the training on the fly, to give a signal on how it will behave in a real world scenario. And if you add that with early stopping, you will be able to interrupt the training before it starts to overfit. Batch normalization has also the ability to the network not to get biased towards the features which has larger values. It normalizes them. That also it does on the fly, but it's done by adding a layer in between. There are some suggestions at the end of this episode on how you can simplify. For example, somebody suggested that like, why should we add all of the cities? So that's one thing you could do, and you can easily do that if you plug this in at the beginning of the notebook, so that we are using just weather parameters from Basel. That's one. We can add more data, like Yonglei was suggesting. Sometimes more data helps. Instead of just 3 years, why not use the whole data set? Keeping some aside for the training and validation. And you should take a look at what the RMSE score is, compare it against the baseline. So if you have time, take a look and try it. And any questions so far, other than what I've mentioned? And if you're really interested, I'll be curious to see what kind of RMSE values you got at the end of the training, just to keep some sort of nice competition. And the baseline parameters, RMSE will be the same, but what did you get yourself? I'll try to do that too. I wanted to get out of the way, so you can have, any comments.
Perfect. Thank you. Thank you very much for amazing presentations and exercises. It was really a pleasure being with all of you today. And thank you, participants, for being here as well. And we are looking forward to seeing you on Monday. For now, you can, of course, continue using Discord and try to rest during the weekend. Enjoy the weekend. See you soon. Bye bye.